Hello, welcome to the online course on pericyclic reactions and organic photochemistry. This is module 22 of this particular course, and in this module we will consider chelotropic reaction, particularly chelotropic reactions involving sulfur dioxide extrusion reactions. In other words, reactions in which sulfur dioxide is eliminated as a neutral molecule during the course of the reaction. Now, the definition of chelotropic reaction is given in this particular slide. A chelotropic reaction is a process in which two sigma bonds are broken, which are originally connected to a polyene system. You consider this molecule here. This is a polyene system consisting of m-2 number of pi bonds involved in the cyclic system. Now, C1A and CMA are the two sigma bonds that are originally connected to atom A with the cyclic polyene system, and the C1A bond and the CMA bond are broken, releasing the molecule which is DAB. So the neutral molecule which is DAB is released in this particular reaction, resulting in the formation of a polyene system which is a acyclic polyene system now, containing m number of pi electron. There are 2 pi electrons more than the starting material because of the electrons coming from the breaking of the C1A and the CMA bond. So I hope the schematic tells you much more clearly what a chelotropic reaction is. Chelotropic reactions are reactions involving elimination of neutral molecules like nitrogen, sulfur dioxide, carbon dioxide, and so on, carbon monoxide, and so on. Now, if the chelotropic reactions can be analyzed in many ways. Now, let us first consider the examples of chelotropic reaction. Here is a reaction of butadiene reacting with sulfur dioxide, resulting in the formation of the sulfoline as the product, which is this particular product. The reverse reaction is the exclusion of sulfur dioxide to give sulfur dioxide and butadiene as the product. This is a reversible reaction. This reaction was essentially discovered during the study of the vulcanization of rubber using sulfur as the cross-linking agent. Sulfur dioxide is invariably produced at high temperatures in the presence of oxygen, and the scientist who was investigating in Dunlop laboratory essentially discovered this particular reaction involving the addition of sulfur dioxide to isoprene, or the elimination of sulfur dioxide from the isoprenyl adduct of the sulfoline derivative, the corresponding sulfoline derivative from isoprene. So this particular reaction essentially involves a 4n+2 number of electrons. In other words, 6 electrons are involved, as you can count from the number of arrows that are shifted in the transition state structure in this particular case. So the 6 electrons that are involved are the 2 pi electrons and the 4 sigma electrons, 2 sigma electron connecting this carbon and sulfur, and 2 sigma electron connecting this carbon and this particular sulfur in this particular instance. Now, cyclic diacenes also undergo thermal elimination of nitrogen molecule. One neutral molecule of nitrogen is eliminated by a same mechanism as it is shown here, for example, resulting in the formation of butadiene. But once nitrogen is formed, the reaction is not a reversible reaction. The top reaction is reversible. It is in the forward direction. It is possible if you have a high pressure of sulfur dioxide. In the reverse reaction, it is possible at high temperature, the continuous removal of the sulfur dioxide. The equilibrium can be shifted in the forward direction using high pressure of sulfur dioxide, and in the reverse direction by the continuous removal of sulfur dioxide that is formed. Unlike the top reaction, the nitrogen extrusion reaction is not a reversible reaction. Nitrogen, once it is formed, it is unreactive. It does not further react with the butadiene to give back the starting material. Similarly, in this particular case, this is a higher homologue of the first reaction that is shown. This reaction involves 6 electrons. This reaction involves 8 electrons in the system. As you can see, the number of arrows that are counted here are 4 arrows are counted. So 4 times 2, 8 electrons are involved in the reaction. 4 pi electrons, which are these 2 pi electron and these 2 pi electron, and 4 sigma electron, 2 of this sigma electron and 2 of the sigma electrons are involved during the course of the chelotropic elimination of sulfur dioxide. Once the sulfur dioxide is eliminated, the reverse reaction does not take place, for example. So this reaction is also not a reversible reaction involving a 8 electron system in this case. The way to analyze the chelotropic reaction, there are 2 types of transition states that are involved in a chelotropic reaction. One is called the linear chelotropic reaction, other one is called the nonlinear chelotropic reaction. In the linear chelotropic reaction, the molecule, which is the cyclic polyene molecule containing the molecule that is going to be eliminated, namely DAB molecule, is confined in a Cartesian coordinate such that the atom A occupies the origin and atom B and D essentially lie in the YZ plane of this particular system. So you can see here in this chelotropic reaction, the B and D are pulled along the direction of the Z, resulting in the formation of the DAB molecule by the cleavage of the C1A and the CMA bond. These two bonds are cleaved during the course of the reaction, resulting in the formation of a p orbital on the atom A along the direction of the x-axis. In the case of the nonlinear chelotropic reaction, this is a nonlinear chelotropic reaction because atom B and atom D are pulled upward towards the x-axis, so much so that at the end of the reaction, the DAB molecule is actually lying on the XY plane, not on the XZ plane. So as a result of that, there is a tilting motion that is taking place as shown by these curved arrows, resulting in the formation of a p orbital along the Z direction. So this is a nonlinear chelotropic reaction and this is a linear chelotropic reaction. One can use the frontier molecular orbital analysis kind of a system to consider the nonlinear and the linear chelotropic reaction and derive the Woodward-Hoffmann rule in terms of conrotatory and disrotatory processes that can take place during the cleavage of the sulfalane kind of a molecule. Now if you consider the HOMO of the nonlinear system or the linear system as the case may be, this is a symmetrical combination of the molecular orbital in the nonlinear system, whereas this is an antisymmetrical combination of the molecular orbital in the linear system. This undergoes a disrotatory process essentially to produce this HOMO of the molecule that is shown here. So this is essentially a allowed process in the if you consider the Woodward-Hoffmann rules, this is a 4n electron system. If it is a 4n electron system, then it is an allowed process in the ground state, in other words under thermal condition, by a disrotatory process for the linear and the conrotatory process for a non-linear. So disrotatory process linear, this is an allowed process. Conrotatory process non-linear also is an allowed process if it is a 4n electron system. If it is a 4n plus 2 electron system, then the nonlinear process will have the disrotatory process, whereas the linear process will have the conrotatory process, which are allowed, which are complementary to each other. So under the thermal conditions, it is very clear 4n electron system will undergo disrotatory motion, whereas a 4n plus 2 electron motion will undergo the conrotatory process for linear chelotropic reaction. In the nonlinear chelotropic reaction, it will be just the opposite. Under photochemical condition, it is complementary to the thermal reaction. When it is allowed disrotatory manner for a 4n electron system, then it is allowed in the conrotatory manner for the 4 electron system under photochemical condition. So these are the Woodward-Hoffmann rules essentially derived from the FMO kind of an analysis which is shown in this particular slide, and the results are interpreted in this manner. As mentioned earlier, sulfur dioxide can react with the butadiene at high temperature and high pressure, resulting in the formation of sulfolene. Sulfolene can also undergo decomposition to give sulfur dioxide and butadiene also. So it depends on how the reaction is pushed. If the high pressure of sulfur dioxide is used, then it can be pushed in the left hand side direction. If sulfur dioxide is continuously removed, then it can be pushed in the right hand direction also. One should see this reaction as a method of storing butadiene, which is a gas, in the solid form. This sulfolene is a solid material. So once solid material is heated, you form the gaseous product. So whenever butadiene is needed for a Diels-Alder kind of a reaction, one can also take the sulfolene and heat it up in situ, generate the butadiene and trap the butadiene with another dienophile, resulting in the formation of a Diels-Alder product. We will see some examples of such reaction in due course. So essentially one can consider this as a solid equivalent of butadiene, which can be thermalized to get the butadiene quite readily by elimination of sulfur dioxide. The reactions are highly diastereoselective in nature. If we consider the cis isomer of the dimethyl substituted sulfolene, in other words 2,5-dimethyl substituted sulfolene is what we are talking about. In the forward direction, it undergoes a disrotatory motion of these two bonds, namely this carbon sulfur bond and this carbon sulfur bond, resulting in the formation of the 2-methyl group being EE isomer of the hexa 2,4-diene is formed during the course of the reaction. The reverse reaction also, if you take the hexa-2,4-diene EE isomer and use sulfur dioxide as the trapping agent, the sulfoline that is formed is a cis-dimethyl sulfoline that is formed. If you take the other diastereoisomer, namely the trans-dimethyl substituted sulfoline, it undergoes decomposition at a higher temperature. Again, in a very highly stereoselective manner, it produces the EZ isomer. The EZ isomer of hexa-2,4-diene, when it is treated with sulfur dioxide, the reverse reaction takes place, resulting in the formation of the trans. In all these cases, this is a disrotatory process that is allowed, and that is what happens in this particular case. So if you look at this reaction, the 4n plus 2 electron system reaction, the disrotatory process is formed. So it has to be a nonlinear chelotropic reaction kind of a system is what we are thinking. This is a 6 electron system involving 2 pi electrons here, 2 sigma electrons and 2 sigma electron. Overall it is a 6 electron system, so it is a 4n plus 2 system. 4n plus 2 system under thermal conditions, when it undergoes a disrotatory process, it is clearly a nonlinear chelotropic kind of a reaction. If we go to the higher order system, the higher homologue of this system, sulfur dioxide extrusion is the process that takes place in a highly diastereoselective manner. This cis isomer here gives the EZ isomer of the octatriene molecule. Octa-2,4,6 triene molecule is what we are getting in this particular case. On the other hand, the reverse reaction is not possible. This is occurring by a conrotatory process involving a twisting of this carbon-sulfur bond and this particular carbon-sulfur bond, resulting in the formation of this particular product. On the other hand, if you take the trans-dimethyl derivative of the higher homologue, which is shown here in the bottom, that undergoes the decomposition at a higher temperature, again in a highly diastereoselective manner, resulting in the formation of the EZE isomer of the octatriene product, which is this particular product in this case. So the reactions are highly diastereoselective. They undergo either in a disrotatory fashion or a conrotatory fashion. If you see the disrotatory process for a 4n plus electron system, this is very similar to the electrocyclic selection rule or electrocyclic Woodward-Hoffmann rule. In the electrocyclic reactions also, a 4n plus 2 reaction under thermal condition will be disrotatory favored. A 4n plus 2 electron system will be, a 4n electron system will be conrotatory favored. A 4n plus 2 electron system will be disrotatory favored, essentially correlating the electrocyclic reaction to the chelotropic reaction by means of a Woodward-Hoffmann rule. Whatever the electrocyclic reaction Woodward-Hoffmann rule applies to the chelotropic reactions also in this particular manner. Now this molecule, which is a bicyclic sulfone molecule, undergoes extrusion of sulfur dioxide at a very high temperature of 300 degrees, perhaps involving a non-concerted pathway involving stepwise breaking of the sulfur carbon bond. The reason being that if it is a conrotatory process, it would involve the formation of a trans-cyclooctene kind of a product, octatriene kind of a product, which is not a geometrically favorable system. So the conrotatory process, which is a symmetry allowed process, does not take place readily. At a higher temperature, a non-concerted pathway is what is proposed for the formation of the cyclooctatriene in this particular instance. So this is not a sigmatropic reaction. The sigmatropic reaction does not take place, this is not a sigmatropic reaction. This is a chelotropic reaction. This is a non-concerted chelotropic reaction, as the concerted chelotropic reaction is not viable because of the formation of a trans double bond in the product. Here is an example of the sulfur dioxide trapping a orthoquinodimethyl kind of a system. The bencyclobutene on heating will give the ring opening, resulting in the formation of orthoquinodimethyl. This is an electrocyclic reaction which we have already studied in the electrocyclic chapter. So the quinodimethyl intermediate that is formed is trapped by sulfur dioxide to produce the bensulfoline as the product. This is in fact a very efficient process for trapping of the orthoquinodimethyl derivative that is obtained from the thermolysis of the bencyclobutene, resulting in the formation of a product which is shown on the right hand side. The reverse reaction has been studied by Kawa. The reverse reaction is that if you take the bensulfoline and heat it up to high temperature of 300 degrees Celsius, it forms orthoquinodimethyl. In the absence of any trapping agent, the orthoquinodimethyl essentially undergoes a 4pi cycloaddition reaction, resulting probably not a concerted pathway, is a stepwise pathway probably, resulting in the formation of the dibenzocyclooctadiene kind of a molecule, which is shown here, obtained in 48% yield. In the presence of a trapping agent like the N-phenyl succinimide, for example, this molecule undergoes the Diels-Alder reaction with N-methyl succinimide, resulting in the formation of the cycloadduct in 78% yield. If it is not done in the solution phase, if it is done in the gas phase pyrolysis at high temperature, the orthoquinodimethyl that is formed undergoes ring closing reaction to give the cyclobutene. In fact, the cyclobutene will undergo in ring close. Essentially, this is a gas phase reaction through a flow system probably, where the benzyclobutene is trapped, which cannot further undergo decomposition to the orthoquinodimethyl in a reversible manner. So this is probably a flash vacuum pyrolysis kind of an experiment where the benzyclobutene is trapped in liquid nitrogen trap under the gas phase, resulting in the formation of about 68% of the product with a reverse reaction of this reaction is a forward reaction, whereas this is a reverse reaction. From the benzyclobutene you go to the sulfoline in this case, whereas from the sulfoline you go to the benzyclobutene in this particular case. Here is a higher homologue of the naphthalene system undergoing the the chelotropic elimination of sulfur dioxide to give the corresponding quinodimethyl. The quinodimethyl under the photochemical condition essentially forms the trans diphenyl isomer of the just like benzyclobutene. This is naphthocyclobutene kind of a molecule. Diphenyl substituted naphthocyclobutene is what is formed in this reaction. This is the intermediate that is proposed. Unfortunately, the stereochemical information of the ring opening is not known. It is only the ring closing product that is known. And since it is a Hahn rotatory process, this is probably a ZE isomer is what is undergoing the ring closing reaction to give the trans diphenyl derivative, as one would expect in this case. Norbornadiene undergoes a very unusual chelotropic kind of a trapping. When the high pressure of sulfur dioxide is used, the norbornadiene reacts in a homochelotropic reaction. This is considered as a homochelotropic reaction. The reaction essentially takes place because of the two proximity of these particular bonds, which is inwardly oriented p orbitals are present in the system. We have already seen this in the 2+2 cycloaddition reaction, which gives quadricyclane from the norbornadiene. Here it undergoes a sulfur dioxide inclusion between these two positions with a concomitant formation of a carbon-carbon bond formation in the backside, which is this particular carbon-carbon bond that is being formed. So this reaction essentially takes place at room temperature. When this molecule is heated, it will undergo reversibly exclusion of sulfur dioxide from the cyclic adduct that is formed in the forward reaction. In the case of tetrahexamethylene 2,2,2 bicyclic system, at low temperature when it's treated with sulfur dioxide, a bis trapping is what is taking place with the sulfur dioxide. The bisulfoline is formed essentially as the product of the reaction of this tetramethylene 2,2,2 bicyclic system. First reaction is sulfur dioxide trapping using these two methylene units, which is a hexamethylene group, resulting in the formation of the sulfoline. The second molecule is also trapping this particular hexamethylene derivative, forming the sulfoline derivative from the other side of the molecule. The synthetic utility of the sulfur dioxide capturing by the butadiene is what is illustrated in this particular example. The alpha protons of the sulfoline are highly acidic in nature, and they can be deprotonated by treating with lithium hexamethyl disilazane or butyl lithium kind of a reagent. So once the carbanion is generated, that is nucleophilic in nature, and that reacts in an SN2 fashion with this diiodo compound to give the methylene bridged bisulfoline derivative, which is this particular derivative. You can have the same sulfoline reacting to give this particular molecule that is shown here. Alternatively, it can also give with another sulfoline molecule after the generation of the carbanion here. You treat it with the 1 mole of the iodide to just the mono substituted derivative. Repeat the same process with a different sulfoline, then you get a different sulfoline attached to this. So it is possible to make both symmetrical as well as unsymmetrical methylene bridged sulfoline derivatives of this kind. What is the use of these derivatives? When they are heated in toluene in the presence of pyridine, pyridine is essentially to trap the sulfur dioxide molecule. You regenerate the butadiene units from this system. which are separated by a methylene linker. The methylene linker chain can be varied depending upon the diiodo derivative that is being taken for the synthesis. Once the butadiene molecules are produced, they can be trapped with the dimethylacetylene dicarboxylate, which is abbreviated as DMAD in this particular case, by a Diels-Alder reaction. A double Diels-Alder reaction essentially produces this hexadiene unit, which could be synthetically a very valuable intermediate in many syntheses, because one can take this dihydroaromatic derivative and aromatize them by treating with DDQ, resulting in the formation of a aromatic system that is linked by a carbon methylene chain, for example, containing the ester functional groups in this particular case. The sulfur dioxide trapping of the orthoquinodimethyl kind of a derivative is also used for the synthesis of this kind of derivatives, with our carbazole derivatives. How are they synthesized? You take the dibromo derivative and treat it with sodium iodide. A 1,4 elimination takes place, resulting in the formation of a hexamethylene orthoquinodimethyl kind of a derivative. So a indole orthoquinodimethyl derivative is what is formed here. In the presence of sulfur dioxide, it is trapped at minus 30 degrees, for example, resulting in the formation of the sulfoline, which is actually fused to the indole kind of a derivative. Once this can be used to regenerate the orthoquinodimethyl derivative by simply heating. So this is kind of storing this reactive intermediate in a sulfoline form. As and when it is needed, this sulfoline can be taken and it can be heated to form the intermediate which was originally produced. That can be trapped by different types of Diels-Alder dienophiles. In this particular case, ethylvinyl ketone is what is taken, and it undergoes the Diels-Alder reaction in a regioselective manner to give these two products in 30:70 ratio, this being the major product in this particular case. So this is essentially used for the synthesis of carbazole derivatives of this kind. The orthoquinodimethyl of the indole can also be synthesized by heating this particular lactone. Carbon dioxide is eliminated in this process to give this particular derivative. So what we have seen in this module is essentially an introduction to chelotropic reaction. There are two types of chelotropic reaction, the one involving a linear chelotropic reaction, the other one involving a nonlinear chelotropic reaction. The diagram essentially clearly defines what is a linear and what is a nonlinear chelotropic reaction. Then we looked at several examples of sulfur dioxide inclusion as well as sulfur dioxide exclusion reactions from sulfoline kind of a molecule, and some synthetic applications of the chelotropic reaction involving sulfur dioxide is also illustrated in this particular module. I hope you enjoyed this module. Thank you very much for your attention.